at that, I said, my lights went off in my head. I felt this is an escape route. This is literally an escape route where, of course, the literature, and I'll quote lots of great scientific articles, where they basically say perpetual motion, oh, free energy, but no, of course not. Conservation of energy still applies. They can't admit that this statement is true, but it's already known to be true. So what we end up with is a new corollary of the conservation of energy that says, well, you got to include the zero-point field too. So if you get some energy from it, you may not have to return it, but at least acknowledge the source. And one of the best proofs, there's dozens of proofs of the effect of zero-point energy, is the one that basically can be seen in the laboratory now. As temperatures in the laboratory have become close enough to be fractional degrees, in other words, millionths of a degree from absolute, liquid helium stays liquid. It doesn't freeze. Every liquid, when it gets cold enough, freezes. But something's keeping helium liquid, and that is zero-point energy. There's nothing else available at that temperature to provide energy. And that's what we find. The exciting part about it is that when you remove the temperature dependence, all of a sudden that's the only thing left. And of course, this diagram is the one that I was referring to before, is that normally we see an experimental proof that the Casimir force pushes. It pushes the plates together, and with tremendous force, with an exponential third power and fourth power as the distances change. Now, to illustrate, there's actually a diagram here that's drawn below it. This is supposed to be a cloud chamber picture. And one thing we have to acknowledge is that electron-positron pairs are coming out of the vacuum all the time. And what you see in this particular diagram too, which is not well reproduced in the slide, is a picture of your local electron. Every electron normally has been pictured as a single, perhaps, ball, a sphere. But as a matter of fact, this is an electron that is a sphere, but it's dressed. And the dressing is all the activity buzzing around this electron that is literally attracted to the electrical gradient. And the electrical gradient is something that I'm very excited about, because in any transduction mode you see throughout nature, whether it's gravity gradient, temperature gradient, or magnetic gradient, which I'm exploring now, the gradient itself is how fast it changes over distance. And at this distance, which can be femtometers, 10 to the minus 15 meters, you get a tremendous gradient. It's so big that one particular article, which I cite in my feasibility study, points out that if the gradient's high enough, you'll get decay of the vacuum. The decay of the physical vacuum is actually an article from Scientific American describing this phenomenon. So locally around every electron, every positron, every proton, a charged particle, the gradient's high enough to break down the vacuum. And when you break down the vacuum, it means, just like Paul Dirac said, you get all these negative energy particles coming to life. They literally have enough energy to pop out of the Dirac sea. And this picture, this image of the Dirac sea penetrating, permeating everything, but having negative energy, is the new quantum mechanical, quantum field theory image of what reality consists of. It's no longer the 18th century image of empty space. See, in the 1700s, they thought the vacuum consisted of emptiness. That's where the word came from, vacuos and so forth. Vacuo is a Latin word, and it means to empty things. But they found that when you take out all the gas, there still was stuff there. And you take out the temperature, bring it down to absolute zero, there's still energy there. So this is an important consideration. So think of the fact that there's lots of activity going on in the vacuum, and this has also been regarded as what's called the quantum foam. Now, there wasn't much activity in this area of research up until 1997. And in 97, what we see, January 21st, in New York Times, is that Dr. Lamoureux from Los Alamos Labs performed what he called the most intellectually satisfying experiment with 5% accuracy that proved the existence of the Casimir force for conductive plates. And at the time, this was regarded as they say, a theoretical interest. But the possibility of the universal vacuum might actually be a false vacuum is now becoming an understandable reality. It's no longer a possibility. It's real. And Lamoureux's experiment woke up a lot of physicists who were on the fence wanting to stay in the classical mode, you know. And of course, I keep talking about how quantum mechanics has been like that for years, proposing a new reality to people who want to just think of cause and effect, billiard ball Newtonian physics. Well, it's a new reality out there. Now, the surprising thing is, and I'll refer to this a little bit later, we've found that the galaxies are accelerating away from each other. In other words, there's a repulsive Casimir force on a macroscopic scale. That's a tremendous new discovery. And the existence of this phenomena in the laboratory has also been verified. In this particular experiment, there's many of them, but Physical Review Letters, volume 89, 2002, really has, I would say, several very interesting ways to control the Casimir force. And so what we find, for example, is that the magnetic susceptibility is important. There's also the large range of parameters that are involved. And of course, even for experimental purposes, the permittivity and permeability effectively give you the control in terms of the impedance. So when you're dealing with an experimental environment, in other words, trying to build a black box that works, you might want to consider, as we have for centuries, the concept of push-pull. And so far, we've only got a push, but now we've got a pull. We've got something pulling apart, repelling the same things that originally were attracting it. And it's all due to the impedance within that container. And what we find, and this is very exciting to me, is that there are a number of experiments, and I'm only going to cite a few, but the rest are in the feasibility study. And they're also, this whole study, by the way, is actually on our website. We have a hard copy available, but I've posted the whole thing for public release. It's in Word. You can download it. It's about 180 pages, about 3 megs of memory.
What's the website?
integrityresearchinstitute.org. And it's very technical. I make no bones about that. But what I do this is also my PhD thesis, is I had to follow a form, which led me to do a literature study, a history of the phenomena. So you get built up from storytelling to technical information. So you can read along as much as you can, and then of course jump to the back of the book for the good stuff, the conclusions. And so that's what I'm giving you today are some of the very important conclusions. And this is also another very important conclusion here, is that as the temperature increases, the change of sign of the Casimir force changes. Now, why I emphasize these kind of controls is, as any engineer will know, once you know how to control the system, you can start imagining things that you can do to change one item and get a change in the other. If you want to force something to change and you know the temperature will do it, why not look at some temperature gradient as your input, and all of a sudden you get a Casimir force output. And that's exactly what scientists have done. And they've done it very creatively, as a matter of fact, as you'll see. Now, here's one scientist who, as I say, just passed away about a year ago, who basically was a pioneer in this subject. We looked for years for journal articles like this, and I believe this was 1984. Yeah, I believe 1984. Physical Review B. And the important thing is Robert L. Forward, for years, looked at the edges of science to see what emerging technologies were possible. And what he proposed initially was this could be a vacuum fluctuation battery. And to all of us who discovered this article, we felt, at least they're talking about it in the physical literature. In the phys rev literature, this is an important achievement to talk about zero-point energy there. Now, initially, he thought that this was perhaps a source of zero-point energy, but as it turns out, it basically is a battery storage facility. And what you find is that as you compare the forces on the plates, the Casimir force and also the Coulomb